Okay, now our next topic of study, we have done Coulomb's law in vector form, we have done superposition principle. Acha, please understand, superposition has nothing to do with electrostatic, what you call Coulomb's law. Superposition is when you have many vectors acting at a point, how do you find the net vector that is acting? For our case, it was net force. So today our study is about electric field, and then we start with something called electric field intensity. Let us understand what is electric field. Now for this we go to grade 9. Okay, say grade 9, and grade 9 you had a chapter called gravitation, in which we said if you have a body which has a mass, then the body has got a gravitational field in and around it, right? Gravitational field means if you bring any other body, let's say I bring any other body which has got a mass m1, this body will be feeling a force of attraction due to this body, which is to say force on m1 due to m. So this force is felt whenever you are within the vicinity of a region where the gravitational field of this body of mass m is there. Now you may ask me, how big is that region where that gravitational field exists? That region is from here till infinity. Closer you come, more will be the effect, or more you will feel the gravitational field. Is this understood? That's how satellites are launched. The satellite has to get released from the gravitational field of our planet Earth, and then if it has to land in moon, it has to get into the lunar trajectory so that it gets now into the gravitational field of moon, so that it is now attracted by moon. Because if you remember in grade 9, I used to tell you this is something like a saint or somebody. There is an aura around him to which people get attracted, and more you are near to it, the more you feel it. Or it is the fright of some goon which is felt the more you are near to it. The far away you are, you don't feel it. This was the story of gravitational field. Similar concept is there with electrical field. So if you have the best way to understand is charges, or say I have a charged body. I have a charged body. This is my charged body. So in and around this body, I will have a region where I will feel what is known as the electric field. Electric field is a vector quantity which is given by, denoted by E, and since it's a vector, I'm representing it in this manner. Okay, so the electric field is the space around a charged body. It can be a charged body, it can be a single charge. End of the day, if there is a charged body, there is a space around it where its presence can be felt, where the field can be felt. Or something like what you watch all those conjurings and all, okay, where you can feel that there is a feel of the spirit. So there's a feel of this electric field. And how do you feel this? How do you feel this? The best way to feel it is we bring another. Now, okay, this is a shop, as I say, and it's making delicious food. How do you understand he makes delicious food? Obviously, somebody has to come and eat it, right? So you have to bring that somebody. Now, that somebody in physics is denoted by Q naught. Get your concepts correct. This is called a test charge. A test charge. A test charge is something which will be positive in nature, usually, not usually, always, and its magnitude is infinitesimally small. Okay, its magnitude is infinitesimally small. It's someone who has come to just smell this place. Okay, now why is this magnitude kept very small? The main reason is this fellow in order to taste the food of this restaurant, don't you think the most hungry fellow will be able to tell it the best? So we don't feed him anything, because if you feed him, then there will be loss of appetite. One, he is not allowed to set up another shop here. He has just come to test it. So if it would have some magnitude, it itself becomes a charged body, and it will develop an electric field around itself, which will hamper with the electric field of the region that you want to study. Making it clear now? So this was the prelude to the discussion of electric field. So if I have a charged body, or it may be a single charge, there is a region around it where the the effect of that charged body will be felt. That is known as the electrical field. Now question arises, sir, how big is that region? That region spreads from the body, charged body, till infinity. The more you are closer, the more you will feel it. Yes or no? The far off you are away, you will not feel it. So let's now see how this quantity is defined in physics in this chapter. We define this quantity with the term called electric field intensity. Denoted by E. Now, who is contributing to this electric field? Here we bring something which is known as a Q. Q can be called as a source charge. Source charge. For your study purpose, we call it the source charge. It's the restaurant whose food products you are going to test. Or it can be also contributed by another charge called Q, which is known as a point charge. Point charge. Now, a source charge, maybe Q, usually we denote to something which is like a charge body, and Q is a point charge, a single point charge, right? Electric field is always due to the, it is a phenomenon which is linked to the source charge. Electric field is associated with the source charge. Now, let's say that you want to find out what is the electric field intensity E at a point. Right? Say this is the point, say P, where you want to find out, and there is a source charge out here. Let's make it simple. So how do I make it simple? How do I make it simple? I mean, I'm taking both of these. No, shouldn't do that. So rather I'll say that I have got a point charge Q, and I want to find out that at a point P, what is the electric field intensity? What is the electric field intensity? And Q as a source charge or as a point charge, for the purpose of our understanding, is also taken always as positive. Right? This is a hypothetical scenario that you're trying to set out. Now, for this region, what we will do, we have to bring a hungry fellow. So bring your hungry fellow. So we bring a hungry fellow out here, which is known as Q naught, and this Q naught will be known as my test charge. Test charge. And this fellow will be known as my point charge or source charge if it is big Q, point charge. So ready? Understood? What is the electric field E at P due to the source charge Q plus? This is what you're trying to find out. So the electric field intensity, mathematically, so electric field intensity will be E as a vector, is defined as the force experienced by the point charge. If you see, what was the gravitational field? The gravitational field was the gravitational force felt by the mass that you used to bring. What is the gravitational field? I have a gravitational field, so it is the force. How do you otherwise associate that? What is the electric field strength out there? So what we will say, or say for example in grade 9, the gravitational field strength. So we say there is a body of mass m, let's be a celestial body. You bring another body to it. What is the gravitational force it is feeling per unit mass? So here we say the electric field intensity at a point P is given by the force experienced by this charge. And we say that electric field E is always linked to source charge. Children, this charge plays no role out there. This charge has only come to assess the scenario. So in a better way, I would write that electric field E is equal to F by Q naught. This we are trying to write it in what you call vector form. And I would put a limit saying that Q naught tends to 0. Means Q naught should be infinitesimally small. If Q naught itself has a value, you cannot test the electric field out here because it is itself creating an aura in and around it. So electrical property is linked to source charge, or you can say that it is a property of source charge. Have you understood this or not? Right? So let us assume that that Q naught and Q are actually in free space or vacuum. Okay. In that case, now this is electric field as a vector quantity. So if you want to find out the magnitude of the electric field, the magnitude of electric field will be given by F divided by Q naught. And what is this F? This F is nothing but the electric force which is felt by Q naught, which is given by Coulomb's law that you have already studied. So I can now write this as K Q. Okay, let's find out what is the force due to force between two charges. Q naught divided by R square, right? And then this is the force. Now you're finding electric field, so you should be having your Q naught also out here. And what is R? R is always the distance between the two charges. R will always be the distance between the two charges, right? First we're trying to do it in vector form. So this Q naught will go away. Sorry, I made some mistake, children. Since I've written as K, so it should be K Q naught upon R square, and you have another Q naught. The Q naught cancels. So the electric field's magnitude is given by KQ by R square, where this is the R. Have we understood this? Okay. Now, if you try to see it in vector format, I would say that the electric field intensity is given by KQ, then it will be divided by R square, and it will be always multiplied by the unit vector R. Unit vector R means the question arises, sir, electric field is a vector quantity. What is the direction of the electric field? The direction of the electric field is given by the direction of the force that is experienced by this test charge. Whom did you bring? I brought this test charge. This test charge is going to experience a force, either attractive or repulsive. Now, in our hypothetical scenario, since this is positive, so this will experience what? It will experience a repulsive force. So I feel that on this side will be the electric force. So the direction of electric field will also be the same. Repeating once again, what is electric field? Region around a charge or region around a charged body. How does it impact you? Well, if you bring any test charge in that region, in the vicinity of the charged body, the test charge is going to experience a force. Depends upon what is the nature of this source charge or point charge. For all our study, we are taking it positive. If this would have been negative, then the electric field would have been on this side, and the force experienced is also on this side. So electric field is studied by the quantity called E, which denotes electric field intensity. Electric field intensity tells you what is the force experienced by the force that is experienced by a test charge which is brought in its vicinity. And the test charge is taken such that its value is infinitesimally small. That's why we introduced the limit saying that Q naught tends to 0. So that Q naught itself does not create an electric field out here. An electric field is a property always of source charge. Is your concept about source and point, source charge, point charge okay? Source and points means the same. Point is when it's a single charge. Source charge is something like a charged body, a large amount of charge which is there, and this is like a point charge, right? Electric field is given by F by Q naught. So if you try to look at in terms of the magnitude, it will be given by KQ by R square, and if you try to look at in terms of vector, you will say KQ by R square, and the force always acts along the line joining the two charges, so it would be R cap, right? From here we see, children, this is one expression, vector form, which is necessary for you. Scalar form, which will be helping you in numericals. And another one which will help you in numericals is electric field is equal to force experienced by a test charge. So the force value is always given as Q naught E. You can write this in vector form also or in scalar form also. Okay? Next is superposition again. Is this understood? Can we go ahead? If you still something to copy, please copy, and we'll go ahead. Done? Okay. Now question arises that you saw a very hypothetical scenario that there is one point charge and you brought a test charge. Right? You're thinking that as if when you learn to drive, there will be only one car on the road and your car on the road. It's not like that. There would be many cars on the road. Similarly, when we were trying to study Coulomb's law in vector form, we always took two charges, but it will not be two charges, maybe many charges. And when there are many charges, there will be many forces. Then we try to find out what is the net force using superposition principle. So the superposition principle will come here once again. So let's talk about it once again. The superposition principle. So let's take a scenario, will not take too much of charges. Let's take some, let's have a Q1, which is say positive. Let's have a Q2, which is negative. Let's have a Q3, which is also negative. And let's have a Q4, which is positive, right? And you want to find out the electric field at a point P, which is here. So definitely out here, what you have done, you have brought a test charge out here. So let's mention that there is a test charge Q0 out here. Change the color so that it becomes easy for you to understand. So let's take a test charge Q0 out here, right? The next point would be that we would be trying to find out the electric field due to each individual charges. So we would be definitely finding out what is the line joining the charges. Right, and let's now find out attractive forces will show by green and repulsive we will be showing by say blue color. Okay, now look at Q1. What is the nature of Q1? Positive. Therefore, due to Q1, the force will be repelling on this side. So obviously I would have the electric field which will also be on this side. I'm calling this electric field E1, which is due to the point charge Q1. This is E1. Understood? Then I've got a Q4, which is also a positive charge. So I'll have a electric field E4 in this direction. Acha children, are you able to understand why I'm writing? See, in the previous diagram, we used to write force. Now we are studying electric field. Superposition principle helps me to find out the net vector that is acting when a system of vectors act at a place. Here, what is the vector? Electric field. What was the vector previous class? Forces. So we were considering on force. Sir, who gave you the right to draw the arrows in this direction? Well, this charge will face a force in this direction. So the electric field is also in this direction, right? After this, what do? After this, I take my negative ones. So I would find that there will be an attractive force called E2 on this side. And similarly, there will also be an attractive force E3 on this side. Is this understood? So the net electric field E, what is E? E is the net electric field intensity. This is the net electric field intensity at P. At P, and I should show my point P also. This is P due to a system of charges around it. And what are the charges, children? Q1, Q2, Q3, and ... Say we would have something up to Qn. Okay? So this E will be now given as the vector sum of E1 plus E2 plus E3 ... plus En. So again, somebody tells you, what does the superposition principle for electric field intensity signify? The superposition principle for electric field intensity gives us the net force, the net electric field at a point with a lot of point charges around it, where the net electric field is given as the vector sum of the individual electric fields due to each point charge taken one at a time, considered one at a time. If you consider it, very easy. Now you will be able to write. English, you know. Once you have understood the head and tail of it, things don't become that difficult. Is this fine? Chatak, epsilon 0 का value कितना है? What is the value of epsilon 0 for free space? What is the expression for Coulomb's law? R1 R2 divided by Q square. Good. Okay. Now we go to properties of electric field lines. Let us try to understand some and then we will write our properties. So if you see magnetism, we had magnetic lines of force. Now we will have something called electric field lines. What are electric field lines? Artificial or imaginary lines and curves which are introduced to find the intensity at a point. What was magnetic field lines of force? Try to remember grade 10. Magnetic field lines of force used to tell you about what is the magnetic field intensity at a point. More is the concentration, more is to be the magnetic field. Then the direction of magnetic field at a point. Then we had some properties. They used to originate from North Pole and terminate at South Pole, right? And then we said no two magnetic field lines cross over each other, because if they cross, then at that point there would be two tangents which shows two directions, as a result of which there would be two directions of magnetic field for the same point, which is not possible. Exactly same things will fit here, but there is a small concept. In magnetism, you don't have the concept of unipole. Means a North Pole does not exist independently, nor does a South Pole exist independently. Whereas in the case of electric charges, unicharge is a valid concept. Means a positive charge can exist and a negative charge can exist. Another difference which we will see is that in a magnetic substance, I would say a bar magnet, you have a positive North Pole and a South Pole. So you see magnetic field lines as a loop, closed loops. Electric field lines won't be closed loops. Okay, so let's understand what is electric field line. Okay, our next topic is electric field lines. And then we will write about its properties. Now just understand and draw diagrams that I'm drawing. Don't write these statements. I will dictate and you can write at that time. Okay, now just try to understand. Whatever text I'm writing, don't worry on that. I will dictate. But whatever figures I'm drawing, try to understand those. What are electric field lines? They are curves or they can be lines. And why? These are all imaginary. Or these are hypothetical. They have been introduced. Why have they been introduced? Introduced to give clarity on A, maybe electric field intensity, okay, and B, also electric field's direction, okay, C, electric field intensity comparison between two points in space. Okay, they can also represent something which is known as suppose the charges have been hidden from you, but the electric field lines are shown. Then you can also decode nature of charges. Let's see one by one each of them. Okay, did you understand this? I will not show the charges to you, but I'll show you electric field lines, and looking at those electric field lines, you will be able to say what are the charges associated with it. So in electricity or electrostatics, we have the concept of what is known as unicharge. So let's take a positive charge and let's take a negative charge. Now you ask yourself, there is an electric field in and around in this blackboard, right? Now consider that this is your test charge, which is positive. what will be the force felt on it due to the electric field? Repulsive always. And what will be the force felt on this negative charge? Okay, another way, consider this as a source charge. Bring one test charge out here. This is my test charge, right? This finger is test charge. What is the force it will feel? Repulsive. What is the force the test charge will feel? Attractive. So we say electric field lines always come radially out from a positive charge. These are electric field lines. Okay. Electric field lines will come out radially out of a positive charge. Children, to understand this is very easy. Whenever you have a problem, you just bring one test charge at this point Q0. What is the force it is going to feel? It is going to feel the force on this side. So that's the electric field. We said electric field intensity's direction is always given by the force experienced, and they will always end on a negative charge. Right? We will write these. Don't worry. We'll write those. Now you understand. Then the next part is, you will not find loops out here. Loops, you understand, like butterfly we used to have, butterfly wings like loops we used to have. So if I have a positive charge out here and if I have a negative charge, I would definitely see the electric field in this direction. Clear? Okay. If I have two positive charges, then the electric field will be in what manner? This manner, this manner. And here the electric field will come out this way because they are repelling each other. Understood? It would be the same for two negatives also. We also talk about, so let's see, does it tell you about direction? Now, how does it tell you about direction? Suppose there is an electric field line which is going here and you want to find out what is the electric field intensity at a point P. So you just draw a tangent at P. The direction of the tangent will tell you the electric field intensity. So electric field direction we have addressed. Okay. Now, nature of charges. Nature of charges. Suppose an unidentified charge is given to you. This is an unidentified charge, and they are saying that the electric fields are all terminating on it. Tell me, children, you'd be able to tell the nature of this charge? Negative charge. Negative charge, right? So this is also what we have addressed. Electric field intensity, nature of charge, and comparison. Now, how to see electric field intensity? Look. Say suppose there is an electric field lines pattern in this manner, parallel. So if you have parallel electric field lines, then we say that the electric field E is uniform. Uniform, whether it is at this point, this point, this point, this point, every point it is uniform, parallel. Clear? If you have electric field lines which are like this, right, and you try to identify two different points, let's say I have taken at one point here and I have taken one point out here. Okay, it's another point here. Where do you see more concentration of electric field line? The green one. The green one, right? So let me name them also. Let's say this is P and let's say this is Q. P has more electric field intensity than Q because the concentration is more out there. If you sample out, say if I sample out equal circles out here, then if you see there is more concentration at P. Understood? So we get a lot of simple questions on this. So can we write now what are electric field lines? So you can write it. Electric field lines are, you can write curves or lines drawn around a charge, curves or lines drawn around a charge in such a way that tangent at any point on them, understand and write, that tangent on any point on them gives the direction of net electric field E, gives the direction of net electric field E. That E you can put in bracket. E means you should write E as vectors, okay? E with an arrow, net electric field, and now you write that E in brackets, and it will be then succeeded by the word intensity. So you're trying to write net electric field intensity, net electric field intensity at that point. And now read, it will make sense. So the definition goes like this: curves or lines drawn around a charge in such a manner that tangent at any point on them gives the direction of the net electric field intensity at that point. And to denote the net electric field intensity, you actually wrote the word E with bracket, right? Now let's come to properties. Come down to properties. Properties, and write the first property. Write the first property. Originate from a positive charge and terminates in a negative charge. Children, I'm not making them grammatically full sentences because I believe with this you will understand and you'll be able to write. Originate from a positive charge and terminate in a negative charge. Right. One point that I missed was, for a single charge, you can write down in the continue in the same point. For a single charge, have you written properties? The first property you have written, originate from a positive charge and terminate in a negative charge. Further you write, for a single charge. Acha. Now look at me. Where can the single charge be? The single charge can be at infinity also. So we write, for a single charge, they may originate or end at infinity. They may originate or end at infinity. They may originate from or end at infinity. Did you understand this line? If your charge is at infinity, it originates from infinity. If your charge means, if your positive charge is at infinity, if a negative charge is at infinity, then it terminates at infinity. Clear? Our next point. In a charge-free region, a region which does not have any charge, charge-free region, electric field lines can be taken as continuous curves without any breaks. Electric field lines can be taken as continuous without any breaks. That means there is a charge, and then from the charge you are moving to a point, and between that point and charge there are no other charges. It's a free region. There the electric field is something like this. Look, this is the charge, and suppose this point is some 500 meters away and there is no charge in between, then it's a continuous line. You won't see any break. If there is any charge which is again coming in between, there might be some breaks in this. Break means a scenario like this. Okay, next point. Two field lines cannot cross each other. Now this is a question. Two field lines cannot cross each other. Cross each other. Okay, we will be writing it in points manner. Have you written two field lines cannot cross each other and then put a greater than symbol, means the next justification. Just a greater than symbol like this. That's like a justification symbol. Two tangents will be there at the same point. So you can, are you understanding what I'm trying to say? You can join these two sentences using your own grammar. It is like this. See, two field lines cannot intersect each other because two tangents will be formed at the same point. Two tangents will be formed at the same point. Again, put a greater than symbol. These are all our arguments. Two directions of net electric field intensity at the same point. Two directions of net electric field intensity at the same point. Two directions of net electric field intensity at the same point. Fine. Again, put a greater than symbol. which is not possible. Now you can stitch up all these points to make your argument. Two electric field lines cannot cross each other, because if they do, then at the point where they do so, you will come up with two tangents which show two electric field intensities directions for the same point, which is not possible. All right. Our next point would be, do not form any closed loops. Do not form any closed loops. Do not form any closed loops. Next point, equidistant field lines represent uniform electric field. Equidistant field lines represent uniform electric field, and vice versa. That means if they say that this region has uniform electric field, then your sketch should show equidistant field lines. Are we fine? Okay. Our last point, density of field lines is directly proportional to intensity of electric field. So the more intense your electric field is, the more dense would be the more intense would be the electric field. Done. So far, what did you study? You studied electric field intensity. You understood the concept of electric field. So for electric field, that it is the aura of a charged body or a charge. Such charges are called either source charges or point charges. To test them, we bring a test charge. A test charge is such that it is always positive. Magnitude is infinitesimally small, brought so that it does not hamper the electric field of the region what you want to measure. Then we found out what is the mathematical definition. Electric field intensity is given as the force experienced by the test charge. E is equal to F by Q naught, and E in expression way, scalar format, we say it is KQ by R square, where Q is the point charge or the source charge. After that, what did we learn? We also learned that the electric field acts along the line joining the two charges, and the force, whatever would be the direction of the force, the same is the direction of the electric field. Then we understood that if you want to find the electric field at a point where there is a system of charges, then you use superposition principle to find out the electric field due to each individual charge taken one at a time, and your point charge and your test charge, and then you make a vector sum of all the electric field. Then we brought out the concept of electric field lines, some imaginary curves or lines which are drawn to basically address these things, like what is the polarity of the charge, what is the strength of electric field at a point, then what is the nature, whether it is uniform or non-uniform, then how do they originate. Always remember, they originate out, radially out from positive, and they will be all terminating in. And if it's a single charge system, it can also be at infinity, because the charge can be at infinity. And if you have a free space, the electric field line will pass that free space always with a continuous line, no break, and two electric field lines do not cross each other. Brings you to your first derivation for this chapter now. So we are going to do a derivation for electric field intensity at a point on the axis of a uniformly charged circular ring. Now this is something like your hula hoop. You have a hula hoop now which is uniformly charged, and then you are going to find out. So there can be two diagrams. Let's appreciate each diagram so that you have no confusion. Otherwise you'll say, sir, in book it was like this. So let's say that this is the axis This is the axis of what? A uniformly charged ring. Are you understanding? Right? If you have any trouble to understand this, you can understand in this manner also. This is your ring and you should be having an axis around it. This is the axis. Your job is to find out the electric field intensity at a point on the axis. This is the axis. So there will be some point out here. So let's say we have a point which is P, right? And similarly, we should, if I go by this diagram, then this is my point P. Any one diagram is sufficient. I have made two diagrams just for you to understand. Okay. Now this electric field, this ring is uniformly charged. This is uniformly charged. So there was charge Q, and this Q charge is uniformly distributed. Bacha, are you able to understand this concept or not? Right? It is like one lump of butter which you have uniformly spread. So let us spread it here also. Why should you make this ring unhappy? Fine. The ring has a center O and this ring has a radius. The ring has a radius and the radius is given by A. The radius is given by A. The radius is given by A. So this is O and this is A. Right? This is A. Clear? Our point P as now P will be at a variable point. You don't know where it is. It can be here, it can be here, it can be here. So this quantity is varying. It is at a distance X. P point is at a distance X. Children, it is getting recorded. So when you write your notes, you can write those statements. Let Q charge be uniformly distributed, or you want me to write these parallelly? Okay. So Q charge, this is one point. Q charge is uniformly distributed, point number one. Okay, let's say, sorry, point number one, Q charge is uniformly distributed over the ring. Okay, distributed over the ring, and the ring is such that it has a center which is O and a radius equal to A. Clear? And at a point, this point is nothing but P is at X from O. Clear now? P is at X from O. Fine. Now we have to find out what is the electric field intensity at P. Now in order to find this, since this is uniformly distributed, so what we have to do, we have to take small portions of this ring. So what we do, we take two small portions of this ring which are diametrically opposite to each other. One is this portion and one is this portion. Diametrically opposite. Sir, why have you taken diametrically opposite? You will understand slowly, just within some time. Diametric. And these portions contribute a charge which is dq. dq is a small charge element. So what is dq? dq is a infinitesimally del q rather small charge element of the ring. Okay, what we are trying to understand, the ring has got many such infinitesimally small. Imagine that this is a rosary bead, so each bead is a dq. All dqs will contribute to q. Q has been spread as dq. So all dqs will be contributing to something which is known as q. Understood? We have taken two such dqs which are diametrically opposite to each other. We have taken diametrically opposite. Acha, are you able to visualize this? What is diametrically opposite the ring? One on this side, one on this side. So this is a DQ region, this is a DQ, and this is a DQ, right? Now just understand, if you want to find the electric field out here, what is electric field at a point? Force divided by the charge. Force divided by this charge. So it is given by K. Now this is your charge. So KQ by R square. Now your R will be what? The distance from what? The distance from DQ to P. Do you agree or not? So we need to now also plot the distance from DQ to P. So let's plot the distance of DQ to P. So DQ to P is something like this. And if I want to plot it on this diagram, yes, it is this. Similarly, from the other one also you will have one, this. Here I am not drawing from the other one. Okay, if you want, we can draw. Not an issue. Let's draw. Fine. Now, what do you think should be this? The R that you have, what is its length? Tell me. Its length should be a square plus x square root. Agreed? So here also we'll write a square plus x square under root. This has come from Pythagoras theorem. Now the test charge here will be positive, whatever test charge we have put. So what is the electric field's direction? It will be away from this line. So let's put our electric field's direction. My electric field's direction would be now in this direction. Clear? And similarly, for the bottom one, the electric field direction will be away from that. Clear? So you would have electric field direction in this manner. Many people just mug this up. Why should you mug up if your concept is clear? Okay. And these electric fields are due to very small, what do you call, charge element dq. So I will tell that these electric fields are dE, and this is also dE. Agreed? Fine. And let them make an angle theta each with here, theta. So this side also what we are having, theta and theta. Agreed? We have a theta here and a theta. Obviously the angle will be same. You are trying to draw it like a from the diametrically opposite points. So this is dE and this is also dE. Children, at this point, if you have not understood anything, we can still revise once again. Anything that is going beyond your head. All fine? Okay. You want to find out the electric field at a point P. Now, what we said, superposition principle. This is one electric field, this is one electric field. So in superposition principle, whenever you do vector addition, ultimately what will you do? You will try to find out what are the electric fields on the X, what are the electric fields on the Y, right? So our time now to resolve these electric fields, okay? So let's resolve these electric fields. Now pay very good attention. If you look at DE1, this is, say if this is DE1, then this will have a horizontal component which will be in this direction called dE cos of theta. Is this understood or not? Fine. Again, for this one also we will have another one which will be same. For this also we will have dE cos of theta. Just for your understanding, right? If this was dE1, then this is dE1. If this was 2, then this is 2. Just for understanding. But I'm taking away the 1s and the 2s because the values will be same, because both are originating due to the distance is same, the charge element is same. So in this diagram, if I try to make that, then along this, I would have something which is known as dE cos theta, and I would have another dE cos theta, where this angle is theta and this angle is theta. है ना बच्चा? Till this much is okay? Similarly, I will also have vertical components which will be on this side called dE sine theta, and I'll have another vertical component here which is dE sine theta. And if you want to see it in this diagram, then it will be dE sine theta, and this one will also be dE sine theta. Children, don't you think the dE sine thetas cancel each other? Right? They cancel each other. Now start putting your ideology. They cancel each other for this diametric position. If the diametric position is like between 2 o'clock and 8 o'clock, then also they will cancel. The hula hoop is like this. If these two cancel, these two also cancel, these two also cancel, these two also cancel, these two also cancel. That means we can write a statement here that all dE sine theta component from similar diametrically opposite elements cancel each other. Cancel each other, right? And net electric field E at P is contributed only by dE cos theta component. Agreed or not? Now, since you are seeing 2, so you will say, sir, the net electric field is 2 dE cos theta. But children, there are many dE cos thetas. Yes or no? So I'm not changing the E net, the net electric field at P now will be given as the integral of, the integral of dE cos theta. Means dE cos theta, dE cos theta, dE cos theta, all these we will be integrating. Fine. Cos theta being a constant comes out of the integral and it is now dE. Agreed? Okay. Cos theta being a constant remains outside. dE is K dQ by R square. What is your R square? A square plus X square. R square. This is R square. Right. Can I go further, children? Now let's see what are the constants out here. A square X square has nothing to do with the integral. The integral is over dQ. So K A square X square cos theta all come outside. So we write K cos theta A square plus X square. Achha, children, don't confuse here. Many children will say, sir, how did you take X outside? Well, my integral is not with X. My variable is dq. My variable is dq. ठीक है? And I'm begging for some space because I don't want to change the screen. So I can now write E to be equal to, if you integrate this Q dq, what do you get? Q, electric field intensity at a point on a uniformly charged ring. What is this Q? This is the Q charge. Q, K I am retaining as K. Cos theta, what is cos theta? Adjacent side by hypotenuse. X upon root a square plus x square cos theta. This is multiplied by another a square plus x square which was already there. Do you agree or not? K, a square x square integral, right? So now E can be expressed as kqx a square plus x square to the power 3 by 2. Right? Fine. Which tells us that electric field intensity always, now quickly, we have short of time, so let's understand. This is the scalar component. This is the scalar component. If you want to now present this in vector form, then in vector form we have to mention this as some vector r, some r, and then I will write this as E in vector form will be, children, now you know everything about vector, kqx divided by r square, r to the power not square, r 3 by 2 r cap along that direction of the vector. Now a question arises, what is the electric field intensity at the center? When you come at the center, x becomes 0. So electric field intensity is 0. Because that center, what is happening? Center, all the cos thetas will cancel each other, all the sin thetas will also cancel each other. This derivation must have been done in your school also. But they will not do this two diagrams and that color to make it easy. Has this gone in your head? Now you can easily make it, not make it, you can explain anyone. What do? We take a ring where a lump of charge Q was spread uniformly. And you want to find out on the axis of this ring at a point P, which is at a variable distance x, what is the electric field. You take two small chunks out from here which are called dq, and you want to find out what is the electric field due to these dq diametrically opposite. But keeping in mind that this ring has got many such diametrically opposite. Whenever you take a diametrically opposite scenario, you have a radius, you have a length. So this is the distance now. Children, in terms of Coulomb's law, this is one charge, this is one charge. The force is along this. Therefore, this is important for you. And you get dE. This dE can be further broken as dE cos theta, dE sin theta. This is dE because you took 2. So here, if there were n, there would have been n dE cos thetas, n dE sin thetas. All will cancel each other. Achha, are you able to understand? Sometimes sin theta will be like this. Cos theta will be, sometimes sin theta will be like this, the other sin theta, because you're taking different positions, and then they will cancel out, and then you get it. And from here there will be one question which will be, what is the electric field intensity at the center? At a center it will be always 0, because x becomes 0, this becomes 0. Our next topic would be, what is an electric dipole? And then we will find out what is the electric field intensity at a line on the axis of the dipole, at a point on the axis of the dipole, and at a point on the equatorial plane of the dipole. A dipole is something like this, plus q minus q, separated by 2a, a on the center. Then when we say on the axis, that means this is this line joining. It can be on this side, it can be on this side. And equatorial plane means join these two, make a perpendicular bisector. That is the equatorial plane. There you are going to find out. Equatorial plane is like putting one plywood through my head, and on that plywood you are trying to find out what is the electric field. Fine. I think these are